It is. It is. That is a big problem. Yeah. But it's also a question of how steep the variation in the potential is.
For the bulk-in tolerance,
yes.
I remember it has a structure transition.
Yes.
The function of temperature.
Yes.
And neither the low temperature nor the high temperature is not an ideal FCC lattice.
Yeah, so wait a second. This happens as a function of composition.
Right, so the initial part, your first part,
yeah.
I think I understand that you dope, well, not a doping, I mean, you put some alloy of the lead telluride and
yes.
spin telluride, and by doing so, you move from trivial to topological.
Yes.
Is there any way the structure transition associated with it? Because with the ideal FCC,
yes.
if you do the band structure calculation, you don't get the CTI.
So the structural transition happens at a different composition. So everything that I showed you is only happening on the surface for the tin doping of lead tin selenide. But there's definitely a structural transition. At the other end, it's orthorhombic. It's called ortho 62.
Yeah.
It's a completely different crystal structure, and it's not topological.
So in the thin film, did you specify the structure of your film, the second part?
No. We believe that at 40 monolayers, it's probably just cubic.
And
the bulk.
Okay.
The bulk. And we have these surface states, so not
that will mirror symmetry because it's a TCI.
Not necessarily. The bulk might have mirror symmetry, but once again on the surface, it's likely that it's broken. All the measurements we make are far from the Dirac point.
What? I don't understand.
So the earlier part of the talk you showed that the symmetry is broken at the surface.
Yes.
Not all symmetries, but
one.
The vacuum, so it led to two of the stones being gapped out.
Correct.
Is there some way to restore that symmetry while remaining in the topological band structure in the bulk by doing some, so that you can drive a transition between, so there is a bulk transition. The main bulk is always topological, but you are driving a transition between, say, two Dirac cones to four gaps.
I mean, that's a great question. I can't see. So you can try and apply strain.
Right.
But imagine the kinds of energy required to imagine how much energy you would need. So the reason that the surface does this, I believe, is because this structure is the lowest energy structure for the surface. Right? Because the surface is a broken symmetry. Now, if you want to change that, I don't even know how much energy it would be. Maybe temperature could do it. Yeah.
How much?
Other questions? So, Vidya, in the first part you talked about spectroscopy. Could you just QPI without mentioning see all that beautiful little plant structure?
Yeah, so we can do QPI. The problem with, and we have actually, and I didn't show it to you. The problem with QPI is, in CI the problem is because of spin texture close to the Dirac point, you have prohibited backscattering and you have no signal. In CCI the problem is you have four Dirac cones, and so you can have scattering in between the Dirac cones, but that signature remains unchanged. It doesn't change until you get to the Lipschitz condition. Meaning in QPI, all you'll see are four dots, and you keep seeing the four dots until you get to the Lipschitz transition. And then you get information, but that's useless because we're interested in the Dirac distortion.
Okay, if there are no other questions, let's thank Vidya again.
Okay, so I'd like to start my talk by thanking the four organizers and chief scientific advisors for inviting me to this wonderful workshop.
I really enjoy the workshop and to meet with my friends and to have stimulating discussions during conference, and especially for escaping from super hot, super humid summer in Tokyo for this beautiful weather in California. So my name is Yuki Motome from Tokyo. Today I'm going to tell you about our recent progress. This wonderful workshop. I really enjoy the workshop and to meet with my friends and to have stimulating discussions during the conference, and especially for escaping from super hot, super humid summer in Tokyo for this beautiful weather in California. So my name is Yuki Motome from Tokyo. Today I'm going to tell you about our recent progress in quantum Monte Carlo simulation studies of p-type model. So actually we had many talks on Tuesday in this conference on p-type physics. I'm a little bit split off from that session, but I will talk about p-type physics in this one. So, okay, so here is the message of this talk. So quantum simulation is one of the most interesting things not only in condensed matter physics, but also recently in quantum information or some so-called computation. And the p-type model provides us a very beautiful example of quantum simulation in the ground state. For example, in this kind of 2D honeycomb lattice or 3D hyper-honeycomb lattices, we had many stories about that on Tuesday. So, but the problem is that all the candidate material so far shows some long-range order at low temperature. So, this kind of genuine exact quantum simulative behavior is hindered by long-range order in all the material. So our fundamental question here is this the end of the story of the quantum simulative system, or is there no hope to see the kind of quantum simulation? And our answer is no, and there are many manifestations which can be seen at high temperature, even at high temperature paramagnetism. So, as we have heard in many talks in this conference, so many studies have been done ground state by adding many perturbations to the pure p-type ring, like Heisenberg exchange or diagonal exchange, further neighbor intermediate. So, all these kind of perturbations induce some long-range order. So this quantum simulated behavior is rather larger against the perturbation. But here we want to give some different point of view by adding temperature. And of course this is very very safe, but what I want to tell you here is that we see some proximity to quantum simulation. Even if we have some long-range order state at low temperature, if the depth of interaction is low. So what I want to show here is that some manifestation of the fractionalization of quantum state as an indication of quantum simulation and type of quantum simulation. And I want to show you our expressive proof quantum calculation for the physical observables like sensitivity, incorporation, magnetic dimensional capture. So, yeah, at this stage, we are working on this on the finite temperature region that really, but we believe that this so far it can be extended to free. And also, after showing this manifestation, I want to talk more exotic things from the theoretical point of view in this region, in this low temperature region. So I want to show you some exotic quantum simulation, quantum simulation, paramagnetic space transition. this for equal. Okay, so these are my collaborators. So the main player in this project is Dr. Shinjyuku, who was the former